Oh, so those who are watching a video, hello, I'm David. Now you've seen my face, you've probably heard my voice a lot, but now you know what I look like. That's enough of me on the screen. After several years, I will then have all the revision seminars will have my face at the beginning, and I won't have that problem of people walking into the Math Learning Centre and say, your voice is really familiar. Do you do the revision seminars? So that's it'll take a few years to replace all the old ones. All right, I promised several people that I'll do Laplace transforms, and it's the only topic left in the course that doesn't have any revision seminars in it for it. And also for future students, hello to you if you're listening, who are doing dynamics and control and have to do Laplace transforms before they do it in Eng Maths. I'm hoping this will be useful for you. So, yes. But I apologise now for anything that is slightly dodgy, because, as you know, for most of the things that are differential equations, I didn't study them formally in a course. So I've done remarkably well considering that, actually. So there is hope for you. So Laplace transforms are a thing that you do to functions, and the major purpose of them is, in terms of why we think they're so useful, is for solving differential equations, because Laplace transforms interact with differentiation and integration in a nice and handy way, which allows them to work on differential equations. So I'm just going to talk through my understanding of them. So the concept is that we have functions.
Do you got a microphone up?
It is actually recording in the microphone. Do you want? Yep. I can see it on the screen. The thing is, we have functions, usually of t, and we can transform them back and forth into functions of s for traditionally it's t and s. And one of the reasons t is, I think, that a lot of these differential equations come up with time as the variable that they're an equation of. But presumably you could do a function of x and you could turn it into a function of s if you wanted, but it's traditional to use t and s. And we can have this transformation which switches functions of t into functions of s and back again, and that's lovely. So in essence, the Laplace transform is a function that works on functions. You stick functions in it and it spits functions out. Great. Whereas you're used to functions working on numbers, and now that you've done Eng Maths IIB, you can do functions working on vectors as well, or functions working on matrices. You put things in and it spits things out, and now we're going to put functions in and spit functions out. And the way that it achieves this relationship is via an integral. And because of that integral, things that you do to functions will have certain things happen to functions of t will correspond to certain things happening to the functions of s. Okay, so that's the idea behind it. I'm making this up as I go along, so please forgive me. I did watch some lectures, and this is the first time ever I have watched lectures online, because they didn't do that when I was a student. I now know what it is to watch a lecture at 1 3/4 speed, because 2 was slightly too fast for me to be able to follow. And I now know what that is, and it was an experience, I have to say. It surprises me. I have a feeling that I don't realise how slow I talk when I'm writing on paper here, because when I sped it up, it seemed like normal speech. So. Yes, now I'm all the self-conscious about how it sounds when I'm writing. But I've now seen it. So I didn't watch your lecturers' lectures. I watched the dynamics and control lecturers' ones, because there were less of those. just like a student. And so I've got a fair understanding, and I've got the notes from this course. So this is my idea. When we learned new functions back in Maths 1A, the beginning of Maths 1A, there was a section of the course right at the beginning where you learned various different functions. And you learned about the absolute value function, you learned about the floor function, and you did trig functions, you did exponentials, you did logarithms. And all of those functions take numbers in, spit numbers out. And one of the things that you did, you may not have noticed it, but one of the things that you did is you figured out how the things that you did to numbers, what happened when you did them to the functions, did the function on those things. And so we learned that logarithms, multiplication inside the log became addition outside the log, and with sine, addition inside the sine is just crap. And so and absolute value can be brought in over multiplication but not over addition, and various things like that. So that's what we're going to do with the Laplace transforms. We're going to say, well, things that we could do to the functions over here, what does that correspond to over here, and vice versa. And from that process, with a very small list of functions that we know the transform of, you can figure out what all the other ones are. And so while it's good to have a nice big list of all of the transforms that are possible, it is possible to figure out most of them from all the rest of them. The same as the times tables, if you happen to know what about half of them are, you can figure out what the rest of them are without having to memorize them. So that's right. I've now talked for long enough. I'm just going to talk it through. So there's a definition. You should always write down the definition. Now, they normally use curly brackets, don't they? But anyway, the Laplace transform of a function is a new function, and I'm going to just get the definition because I can't remember it off the top of my head. So the integral from 0 to infinity of e to the minus st f of t dt. And if you'll notice very carefully, this, by the time you've done the integral and subbed in the 0 and the infinity, the t will have disappeared because you'll end up with something with square brackets, and you'll sub in things with the t, and the t will vanish, and it will now be a function of s. And it's traditional that if you use a little f here, you give that the name capital F. Like that. So that's a definition. And that's what it is. And you can figure out Laplace transforms from the definition if you desire. It often requires you to use integration by parts. Okay, that's the definition. So I don't know how often in an exam things are asked to be done with the definition. Is that common if people have looked at the past exams? I don't get to see the exams because I don't have access to your MyUni site. So are there questions in the past exams that require you to do things by definition? Sorry?
There was one.
There was one once?
2011 or 2012, something like that.
2011 or 2012. So it's not impossible for it to come up, but it doesn't seem likely. Okay, all right. So we can go back to that if we need to. Okay. Right. So there's this great table in the Great Big Book of Everything, also known as Kreisig, which has various things about Laplace transforms. And this is the one that you normally see that tells you it's done in the opposite direction. It has functions of t on this side and Laplace transforms on this side. And there are some classics. And it's good to be able to remember the sequences. And it's also good to ask the lecturer if you get the table. Do you in the exam? Sweet. Does the table have these handy-dandy theorems in it? Like the S shifting and stuff?
Yes.
Okay.
Some of them.
And some of them.
All the ones that you've got there.
Yep. All right, good. Just making sure. That's good. That means that we can support our memory there. It's always good to try and remember anyway, because it makes you faster in the exam. So that's my major piece of advice for maths where you get formula sheets, is try and remember. Okay, so I'm just going to put a couple of them down. A constant function. We'll go to 1 over s. No, sorry, constant function will go to, yep, 1 over s. And a t will go to 1 over s squared. And t to the n will go to something. So normally they write it like this. Like that. Right, so the first thing that occurs to me when I see this list is that it seems to have a pretty strong relationship with Taylor series. Taylor series has x to the n's and n factorials in them, so it seems that if I Laplace transformed a Taylor series, I would get the coefficients of the Taylor series and 1 over s to the whatevers. So it's going to turn all the terms in my Taylor series into s's on the bottom of the same thing. So that's my first instinct. What I'm trying to do here is show you how I go about trying to learn stuff. So, yep. So at the moment, classic. These are our classic transforms. Okay. And then I'll skip the ones with the gamma function in them. They seem a bit scary. And then there's 1 over s minus a comes from e to the at. Actually, I can sort of guess why that's happening, actually. There's like 1 over 1 minus 1 over 1 minus x has a Taylor series that's got all of these things in it. And so I have a feeling that that's why that's working out the way it does. That's what my head is saying. It could be some other reason, but that's the first thing that occurs to me. Okay. And, well, that's probably enough for now. And then there's ones for sine and cos. So sine omega t will be omega like that, let's say. Yep. And cos omega t will be that. Cool. Right, there's some classic functions, and I have a feeling that they're ones that they're sort of the go-to function. You can construct everything else out of them, is what I would suggest. And I know there's a couple of things with like the impulses and stuff.
We've got some Cauchy chine as well, hyperbolics.
Yeah, you're expected to sort of notice those?
They're on the table.
Yep.
Yeah, they're not on the one with that comes with the exam though.
Have you got that with you?
Yes. Would you like it on your screen?
Yeah.
No. We get an abridged version. It's only condensed. It's about like 2 of those, about 10 of them.
So one of the morals of the day is study with other people from your course, because they can tell you this useful information. So we've got...
Plug this in somewhere?
Yeah. Yes, we can.
Do you want a printed copy?
If you've got one. But I do have this as well. It used to. Just until the printed copy arrives.
Assuming we've got the right.
Nope, it's not liking it.
No, I think it's going to take a second. Sorry.
It's okay.
Oh,
Awesome.
that's also good.
Excellent. Thank you very much. So, all right. So this is the abridged version that sort of comes with the exam.
Yep.
Okay, so they're the other ones there that I was thinking about. The ones that go with the step and the, what's that called?
Dirac.
It is called the Dirac, but what was the other word for it?
Delta.
No.
Pulse.
Pulse, that's the word. I knew there was a word. Surge or pulse or something like that. Okay, so they're the other two that we're supposed to know. Whoops, that's the other way around. Okay, cool. So that's our big list of the classic transforms that comes at the top of our thing on in the exam. And the other ones we get are various information about what the transforms do to various things. Okay, and I'm going to think about them in a particular way so that I can organise them. So, over in dynamics and control, the lecturer, yes?
Your sines wants 1 over omega sine omega t.
It's the same thing.
It's the same.
Yes, so that's a good point to realise. The one that I saw when I was looking, so in the book, in this one here, it has 1 over s squared plus w squared is 1 over omega sine omega t. Mine doesn't have the 1 over omega here, but it has an omega here. So the one actually in your notes is this, like that. And so it comes to the same thing. So I'm working from 2 different courses here, which have 2 different lists. So thanks for pointing that out. So it is useful to know, and that's one of the first rules, that if you have to multiply or divide on one side, it'll happen on the other as well, as long as you're doing it with a constant. Okay. So just want to make sure I've got this right. One of the things that the dynamics and control lecturer said, which I thought was kind of cool, was he sort of stepped it up from having the unit pulse, which is this, which is just a pretend function that is infinity at a particular spot, and then the unit step, which is a function which jumps once, and it is this, and then he moved on to the unit like y equals t, and figured out what that one was. And so he had all these different things and worked his way up, which I thought was kind of cool, actually. Right, so you can see already there's some relationships between these things. Okay, cos, which is the derivative of sine, has an extra s on the top. This, which is the derivative of that, like this is the integral of that, and it has an s on the bottom. And this, which is the derivative of that, sorry, this, which is the integral of that, has an extra s on the bottom. So it looks like if you integrate things, you'll get an extra s on the bottom. And so already, just by looking at this list, you can see there's a relationship between derivatives, what derivative does to a function, and what happens over on the transform side. And so that's what all the rest of the things are. So, rules. So, we should be able to construct any Laplace transform from these ones and various rules, and that's the idea behind it. So, rule number 1 is that you can bring that you can expand Laplace transforms out over addition. If you have 2 functions added together, you can just do the Laplace transforms separately and do it before. So adding inside the Laplace transform is the same as adding outside. That's not what I wanted to do. Where's my big eraser? Okay, I'm making it in this list because I don't feel like doing the expanding out version. I just feel like seeing that I've got 2 functions added and I could just Laplace transform them separately. That's what I'm thinking in my head, because when I see a thing, I'm not going to put Laplace transform outside of it. I'm going to do one step at a time. Multiplying a function by a constant. is the same as multiplying the Laplace transform by the constant. So when I see 1 over omega sine stuff equals whatever, it's the same as saying sine is equal to omega times whatever, because I can multiply both sides by whatever I want. If it was 4 cos omega t, it would be 4s. So that's the linearity rule, those two to combined. I can bring out constants, I can expand it out over plus. Okay, so that's what we would normally expect just multiplying by a constant to do with ordinary functions. And that's what differentiation does too. Other things that it does is that multiplication over here is convolution over here. Whatever convolution is. I don't know what convolution is. I've looked at it. There's some integral thing. It looks to me like convolution is one function's going forwards and the other function's going backwards, and you multiply them together as you go. I don't really know what that means, but it's a thing. So basically, as with most things do not expand out nicely over multiplication. We don't even have a thing that if you have two functions multiplied together, there isn't even a thing that goes the other way, as far as I'm aware. If I have like f times g here, it's like, well, I don't know, there isn't a thing for it to go to. Okay, except in special cases where one of them is just s, or 1 over s, and we can deal with that, or e to the whatever. There's a few special cases for that we can deal with. So why don't we deal with that now? So we've got special cases. The special cases of the multiplication are the shifting theorems. Okay? So if you have e to the at ft, the shifting theorem says that. So that's a special case of the multiplication. So we know what to do when we add functions, we know when we multiply them by a single number, we know what to do with convolution if we knew what convolution was, and if you want to multiply two functions together, well, we don't know how it works for all possible functions, but we do know what happens if you multiply a function by e to the at. It does this. So that f is the Laplace transform of little f, by the way. Okay, what's the next? So the other shifting theorem is what happens when you multiply it by a step. I reckon I can fit these all on the same piece of paper. So this is a special case of two functions multiplied together. We have our original function and we've shifted it over, and we've also turned it on at a, which is what the ut minus a means, and we have, and that turns into this. And if you look at it, it's basically the reverse, right? This one tells me if I multiply by e to the at on this side, what it does to the Laplace transform. This one tells me if I multiply by e to the as on this side, it tells me what happens over here. So one of them tells me what happens when I multiply it over in t land, and this one tells me what happens if I multiply by e to the something over in s land. And so trying to forge those connections with them is a useful thing. Okay, so we can add things, we can multiply by constants, we can convolute if we want to, and we can multiply two functions, but only a couple of them do we actually know what to do with. Sweet. Well, there are a couple more that we do know what happens when we multiply them. Let's just see. I'm going to just see what it says in here. I'll deal with that in a second. Okay, I'm going to just leave a couple of spaces for my special cases to fill in a second. For my special cases of f times g, let me mark these as a dot points. Okay. Well, now here's the thing. With numbers, that's pretty much all we can do. We can do multiplication and addition. I suppose we could do powers, but that doesn't sound fun with functions. The other thing we could do to functions is differentiate them and integrate them. And so we should know what that does to the Laplace transform. So if I have f dashed and I differentiate it, what it does is it produces that. So you'll see what happens is that technically what it did is it multiplied by s. We have to adjust it based on what the function value is at 0, but that's okay. A lot of these situations f of 0 is 0, but not always, so just keep that in mind. And f double dashed, well, it'll be s squared. But we will have to adjust it based on what the function values of it and its derivative are as you go. And finally, I'm just going to do the next one just so that I can get the pattern. Like that. So you've got s cubed times the Laplace transform, and then minus s squared times s squared times the original and s times the whatever. And so you'll see what actually happens here is we multiply all of this by f by s and add on an extra term, which makes perfect sense. Like the derivative of this, if we differentiate again, then we should do the same thing that we did here to this. So we have f dashed. Well, when we differentiate it, we'll get that times s, and then we'll take off f dashed of 0. And we'll get that times s, and we'll take off f double dashed of 0. So it's not really something that's necessarily worth remembering, but it's useful to be able to know what happens there. Cool? So that's kind of nice. If we see the derivative of something, if we don't know what the function is, we might have a chance of solving it. And integrals, I'm imagining, should work in the opposite direction. Okay. So if you integrate something from 0 up to t and create that as your new function, then you divide by s. Now we don't have to worry about adjusting it for the function value at 0 because you've already dealt with that by doing the integral and subbing in these two numbers. So that's all already been dealt with. Okay, so that's sweet. Let's see if that makes sense. Go back to our original list. So if I integrate this, I divide by s. Excellent. Beautiful. And if I integrate this, I'll get a half of t squared. Ah, well that's where this n minus 1 factorial is coming from. And I'll divide by s again. And then I'll integrate it again and I'll have to divide by the next power, which is why the factorial is there. All of these ones are coming from integrating that and dividing by s successively as we do. And then this one, if I integrate cos, I'll get sine, but I'll have to divide by the constant. And that's resulted in dividing by s. And so that works. It's working very well, actually. So that's very, very nice. And the integral of the Dirac delta function from anywhere, if you go past the place where it's infinity, the integral from anything from there beyond is 1. So if you integrate it up to that point, it's 0. If you integrate it past that point, it's 1. And so that's a step function. It's 0 everything up to that, and then 1 after that. So this is the integral of that, and that's why this is that divided by s. Sweet. Excellent. Everything's coming together. And that's pretty much everything that I'll talk about at this time, though there is a periodic function thing. Whoa, that's fun. Okay. Right, that'll do for now. Just for me feeling like I've done everything I need to do. So the reason I've talked about it this way is well, at least now I know what's going on. It's good for me. I know bring you along for the ride, but I feel better. And B, I can now point out all of these connections. And every time you learn anything like this, where you do some things and other things and they're related to each other, you should try and find as many connections as you can so that it's easier for you to check your understanding and check your work as you go. And that's why I do all of those things. Now, I did list a couple here, but I don't think that's going to be useful now because we're multiplying. Because when we integrate and differentiate, we're multiplying on this side, not this side. So they weren't as useful as I would like, so I'm just going to run them out. Okay. Sweet. Feeling better now. So the whole point of this was solving differential equations. And so therefore the easiest way is probably to find some questions and do them. So, does anyone have some that we could do, like in a past exam or something?
There's one in there.
There's one in here?
I know that the 2014.
Ah, lovely. Where are we going to look for? Oh, he's helpfully put it in the same order that the course was taught in. Nice. So what's this exam? 2014 yep. Question 1. Okay. Let's read it. A system that is vibrating over time t is described by the initial value problem that, where y is a displacement from the equilibrium position. Okay? Find the Laplace transform of this initial value problem in S space. Okay. So we have y double dash y of 0 is 1, y dashed of 0 is 0. Okay, so we should be able to Laplace transform everything, and note that we can do things with pluses separately. So I can do that one and that one and that one separately, and I can do, the 13 will still be there because the constants just stay there when you do the Laplace transform, and I've got a transform for cos 2t, and the dashes will incorporate these. So let's see. The Laplace transform of y double dash is s squared times the Laplace transform of y I think that's the rule. Let's just check that, hey? S squared times the Laplace transform minus s of the original minus, yeah. Sweet. So presumably I can just use the classic thing of using the capital letter instead of the small letter to indicate that. So that's, now s of y of 0 is 1. So that's s squared y minus s. Okay. And the Laplace transform of y dashed is s like that. So the powers of s go down and the derivatives keep going down. Okay. So that should be s 1. I've got this right. Y of 0 is 1. Yes, just keeping on checking as I go. And the Laplace transform of y is just y, and the Laplace transform of 13 cos 2t would be 13 times whatever the Laplace transform of cos 2t is. So it's got like an s squared plus 2 squared on the bottom, and an s on the top, I think, if I'm remembering correctly. As you say, I'm doing my practicing what I preach. I'm attempting to remember. Yes, okay, I was right. So, right, so what I've now got is that my equation becomes s squared y minus s plus sy minus 1 plus y is 13s on s squared plus 4. Transformed. Sweet. Okay. All good. So presumably I should sort of like simplify that or something. So let's see. We've got a y there, we've got an s squared and an s and a 1. We've got a minus s minus 1. S squared plus s plus 1. So I'm supposed to divide by that s squared plus s plus 1. So does anyone have useful instincts as to whether it's going to be a good idea to put everything over a common denominator or not?
I think you have to solve for y. There was a hint given on the paper though as to what I guess is the partial fraction result. That's what this is wrong.
Okay, so you're right. Further down there's a hint that indicates that. Right. Okay, so the 13s on s squared plus 4s squared plus s plus 1 would happen if I just divided this by that. So it seems like it's not a good idea to put it over a common denominator. Yep.
You definitely don't want a common denominator because of the principle of linearity.
Ah.
You want to be adding things, not multiplying things.
That sounds like a reasonable thing. So for those of you listening online, it's not such a good idea to put it over a common denominator because that would all turn it into multiplication and division, and we would prefer it to be addition because we can do that with Laplace transforms. Okay, good. Okay, so there you have it. That would be part B then, I reckon. Part B said solve for ys equals. Alright. And now we want to back transform this. So we've been given a hint that this bit here can expand out into something else, into that. Okay. Alright. So now what? Let's just do that. Use the hint now while we're at it. So the hint said that the 13s over whatever was equal to this, and so we've split that multiplication into an addition, well, a subtraction.
You made a mistake.
Did I?
Yeah.
The second denominator should be s squared. Sorry, the third one.
Oh, s squared plus 4. Thank you. That makes perfect sense. Otherwise, we could have just, yeah. Thank you. I would have noticed it later, but it's much nicer to notice it earlier. If you can have some sort of Zen watching yourself thing in your exam, then you'll do much better. But you know, having an out-of-body experience during your exam is not necessarily something that's easy to engineer, or might have dangerous side effects. Okay, and it looks like we can at least combine these two into one. That sounds like a good plan. Ooh, that looks very nice.
Factorize.
What's that?
Factorize the denominators.
Okay.
You get into the complex numbers if you do that, though. It's going to be.
All right. So that's a good point. Factorising this denominator would give you complex numbers, so that doesn't sound like a good idea. But something over s squared plus 4, I know what that does. That would be a cos or a sine. So I could reasonably split this into two pieces, and one of them would become a cos and the other one would become a sine. That sounds like a good idea to me. Not sure what to do with this yet, but we'll deal with that in a minute. So one thing that you may or may not have noticed at this point is that I keep forgetting to move my page. And also that you have to recognise things that you know how to do. And so even though you do have a Laplace transform table, it will go much better for you if you can just know, rather than having to look it up. Was that a good plan? Yep. So this we can do. That one will become 1 over 2 sine 2t, I'd say, because we've got an s squared plus 2 squared. The constant we can get rid of, but there'll be a 4, of course, as well. And then the 3s, the s over s squared plus 4 will become a cos 2t. And so we can leave the minus 3 there. So we can deal with them. They're good. This one is the one that we have to cope with now. Now, normally if we could factorise the bottom, we'd do partial fractions to separate it. But that's not going to factorise, I wouldn't say, because the discriminant, like b squared minus 4ac, is negative. So we're going to have to complete the square. Yeah, because the only things that we have, the only things on our list that we have are all of the form something squared plus something. You know, if they've got a squared in them at all, they don't have a constant term. So we have to get rid of the constant term, which means that we have to complete the square. Okay. If you're going to do anything that isn't part of the normal flow of your working, write it down and tell the person who is reading it that that's what you're doing. So let's see. Complete the square. S squared plus 1. So this will be half. So what I've done is I've just, this is how I complete the square anyway. I know it's going to be s plus something squared, and the something is a half of the coefficient that's there. And then I expand it out and I'll get s squared plus 2 times a half times s, which is this bit, plus a quarter squared. And I can't just go adding a quarter there without taking it away as well. And so the s squared plus s plus a quarter becomes this bit, and the 1 minus a quarter becomes 3/4. Like that. So I've now completed the square. Okay. Now my 4s is not going to be nearly as nice as I would like. Now that we've got it as s plus a half, I really need my 4s to be s plus a half as well. So I should sort of complete that one as well. So also 4s is 4s plus a half minus a half, which is 4s plus a half minus 2. So that trick of adding and subtracting the same something is a great trick. You don't have to think. So I saw in one of the examples in your lecture notes that he sort of just magically came up with numbers, but it's much easier for me to just go, well, I need a half, I'll put it in and I'll take it away as well, and then I haven't changed anything. Fergus, one of my Maths Learning Centre staff, calls this a Cinderella move. You say, oh, Cinderella, you would like to have a half. That's okay. You just have to give it back at midnight. And so that's his Cinderella move. Anyway. Yeah, I know. But silly things are memorable. That's my motto. S plus a half minus 2. So I've replaced both pieces of the original y with what they're equal to. The 4s is this, and the bit on the bottom is this. And then I've still got the other bits. If I thought more clearly, I would have just done the Laplace transform separately of each bit, but anyway. So I'm going to separate this into its two pieces. And keep all of these parts. And now I should be able to use plain old ordinary Laplace transforms and shifting theorems. So let's see. So the Laplace transform of this would be 4 lots of... I'm just going to do those bits first. So I'm going to have 2 bits here. I'm going to have 4 of something, and minus 2 of something, and minus 3 of something, and 4 of something. S on s squared plus 4 will become cos 2t. 1 on s squared plus 4 will become 1 on 2 sine 2t. And just to remember, to see if making that correct, if I integrate that one, I'll have to divide by the 2. Okay, yes, that's okay. Cool. So just reminding myself that I need the 1 on 2 there. And now this one, if it was s on s squared plus 3/4, it would become, don't write this down yet, it would become cos of root 3 on 2t, because I do the square root of 3/4. But I've shifted the s. So what happens when I shift the s over? When I shift the s over, I go e to the at. Now I've shifted it with a plus 1/2, so that means that this will actually be a minus 1/2 over here. Okay, so it'll be 4e to the minus 1/2 t, like that. So when you shift the s, you do exactly what you would do as if it was just an s instead of an s plus 1/2, but you multiply by the opposite of the thing that you shifted it by e to the whatever. Okay. Please be... yeah, that was a really weird sentence when I actually think about how it would be written. And then the next one would be a sine, only I've shifted it over. So this would be like 1 on omega, so 2 on root 3 sine root 3 on 2t. That's what that one's going to come to. Only because I've shifted it again, I'm going to have e to the minus 1/2 t. So that's my Laplace, my untransformed thing. So for completeness' sake, I should probably finish it off. So 4e to the minus 1/2 t cos root 3 on 2t minus 4 on root 3 e to the minus 1/2 t sine root 3 on 2t minus 3 cos 2t plus 2 sine 2t. Sweet! Right, that was part C, which started somewhere. Maybe about here, I'd say. About here is where part C starts. Back here when I started to split it up using the partial fractions. Okay. And then part D says, write down the long time solution and indicate how you determine this. So what does that mean? What does long time solution mean?
Assume that those e to the minus t's go to 0.
Yeah. Oh, and we keep the other bit? We're allowed to keep that?
Well, yeah.
Okay. I mean, yes. As t goes to infinity, e to the minus infinity is 0. Okay. I'm going to put, I feel uncomfortable putting an equals, so I'm just going to... And we determine this because e to the minus 1/2 of t goes to 0 as t goes to infinity. Is that the reason?
Yes.
Okay. Okay. since we have to, we have to give it everything that they ask for, or because there's a mark for every part of the question. Sweet, good. Thank you. You see, look at you helping all the other students. You should feel good about yourself. Okay, so it seems to me that that's the deal with ordinary equations, but then there's this other thing with partial differential equations as well, I suppose. Okay. Because I know I saw some partial differential equations, but this exam doesn't have any of that. Do any of the exams have partial differential equations? Has anyone got one of those? So what was that work? How long did it take me to do that? How long did it take me to do that example, do you think? About 15 minutes? And that was worth 12 marks?
Yep.
Okay, that's not too bad. That's only just over a mark a minute. I did quite well. Might have floundered a bit myself because I didn't know what some of the terminology in Part D was, but presumably that's only worth like 1 or 2 marks, so that's not too bad. All right. Where is it? Oh, there it is there. So this is okay. People want me to do part A? Or are we okay with me just doing part B? Because part A looks like it's a completely separate question. Because part A is use Laplace transform to solve this one.
Yes.
That's okay? Cool. In fact, that being equal to 0 sounds nice. Is the Laplace transform of 0 0? Yes, that makes sense. Because it's 0 times e to the whatever, and when you integrate 0, you get 0. Good. That's probably a worthwhile thing to add to the list, just to, for my own purposes. There we go. Now I feel better about that. Okay, so this one says we've got x is distance along a wire, t is time, and voltage is Vxt, is given by the second partial of V with respect to t twice is plus 2 times the first partial of V with t, plus V is the second partial of V with x twice. Okay. Right. All right. Well, I'm going to let people guide me. Presumably, oh, just a second. Subject to v of 0t is sine 2t, and the limit as x approaches infinity of vxt is 0, regardless of what t is. And v0, oh, whoops, sorry, just a second. They were the boundary conditions. And also vx0, I've done them backwards, I'm sorry. vx0 is 0 and dv on dt evaluated at x0 is 0. Okay. Cool. So that's the question. I've written it down now, which wasn't worth probably the effort, but it makes I understand things by writing, so it helps me. By taking Laplace transforms with respect to t and solving the resulting pseudo-ordinary differential equation, that's terminology of the day, show that Vxs, which is equal to the Laplace transform of V, is given by that, where As and Bs are functions that you should determine using the boundary conditions. Okay, so basically they're wanting us to do the Laplace transform and show that the Laplace transform of V comes out something, and we need to figure out what As and Bs are. Okay? Right. I know what Bs is. Sorry, I was making a dad joke. Right. Well, how do we do this? Is there a thing about how different partial, about how different Laplace transforms interact with partial derivatives? My assumption, this is my assumption, and I'm hoping it's reasonable, is that if you're going to transform the t to an s, then anything involving a t will move over to an s, but anything involving an x will stay whatever it is. That's my instinct. Okay? So maybe what I should do is do what I did last time and separately try and do the Laplace transform of each bit. So the Laplace transform of partial d squared v over partial t squared, partial dt squared. And remember that we're doing a t here. I don't know if that's a correct notation, but I just want to remind myself what I'm doing. So v is technically a function of x still, but this should be whatever the Laplace transform of v is, times s squared minus s times whatever the Laplace transform, not Laplace transform, whatever v is when t is 0, but we don't know what x is, minus whatever the derivative of v is when t is 0. That's my guess. Like that. Okay, so technically this will have a Vx0 here. So this will be a new capital V, which is still a function of x, but it's now a function of s as well. And then Vx0 is 0. Okay. And dv on dt of x0 is also 0. Convenient. So s. Okay, so we've dealt with that. So the thing that was important to focus clearly on was the fact that that v is technically a function of x as well as t, and all the x's sort of carry through and just stay there. All right. So the Laplace transform of dv on dt would be s v minus, there's still an x and the t is 0. So we can think of it as v of 0. If we were paying, we can think of it as v of 0, but there is an x there. Okay, so this is s of v, capital Vxs minus 0. Okay. The Laplace transform of just v is Vxs. Good with that. And the Laplace transform of curly d squared v on curly x squared. Well, the derivative of the other function will just pass out of the Laplace transform because of some derivative integral laws that say that the derivative under the integral thing. So we're allowed to do that. So that was, I suppose, something that we could add to our list of things that Laplace transforms do, is that if you differentiate your function with respect to something that the Laplace transform isn't related to, you can just bring that out. So this should be the second derivative of v with respect to x. Sort of x, 0, and a capital V, not 0, s. Something like that. I mean, if you really want to put the x's and s's in, but you can probably just leave it with just the capital V.
Yeah, and wouldn't it be that times the Laplace transform of 1?
I don't know. Is it?
I think that it would be. The Laplace transform of 1 times x. Because you're bringing the differential up from front. So originally it was the differential times 1, so the 1 has to stay inside the transform and the differential has to go on the outside.
Oh, that is interesting, isn't it?
I'm not 100% convincing myself yet. But
No, that's right. So I'm making an assumption here rather than actually reading the notes, which is never a good plan. Given a function defined for all t and assumed to be bounded, we can apply the Laplace transform in t considering x as a parameter. That's the definition. And then when you differentiate it under that, you use integration by parts. So what's going on here? That is that, and that is that. Line them up, mate. Okay. Right. Yep. So when t is infinity, that's 0. And when t is 0, that's 1. And so we get, yep. And this is the Laplace transform. Okay. So when you differentiate with respect to the other variable, you get an s. Right. So basically the same as when you differentiate by, just differentiate by the t. I know that's a t there. Well, yeah, that's fine. That's fine. No, that makes perfect sense. What about the x? So that's saying that we still get an s. Even when we're differentiating by the x. Now this is the Laplace transform as in x. That's the Laplace transform in x. And we're not doing a Laplace transform in x, we're doing a Laplace transform in t. So I think that it just changes. No, look. Let's just see this example here. Look at this. The PDE originally, this PDE here, you've got dw on dt and dw on dx. The little w on dt turned into this bit here, that stuff there. The dw on dt squared turned into this. And the dw on dx just became a d capital W on dx.
Yeah, it says on the second line right there.
Yeah, just there. So, there is a rule here that if this variable is not involved in the Laplace transform, the derivative comes out. And you don't do any s's or any of that other stuff. My instinct was good. Always nice to feel that your instinct is good. So I don't technically need the s here if I don't want to, because I can just treat it as a capital V. I was just doing it for consistency's sake. Where'd my eraser go? Could be anywhere.
You need one?
No, it's all good. I just won't rub it out. And so my equation becomes what did my equation become? My original equation was this. So the curly d squared v on curly dt squared became s squared vxs according to this. And then we've got 2, and the dv on dt became s vxs. And then the v became vxs. That was the next bit here, the v. And then this bit here became d squared capital V on dx squared. Like that. Sweet. Okay. So really it's not that different except for that little move where partial derivatives that are using the variable that's not being transformed just stay there exactly as they are. So what's the next bit of the question asked? Oh, Vx equals, okay. So we have S squared. What are we supposed to do now?
You solve the differential equation for x.
So we solve it for x now. Okay, so we're saying that what we have here, so s is now counting as a constant when we do this differential equation. Okay, clever. Right, so we have so sort of if we think very carefully about, no, I'll do it properly. dv squared on dx squared minus is 0, like that. Yep. Don't know if that was necessary. All right. So in the lecture notes he says we look for a solution of the form either the ux. I mean that's totally like a second order constant coefficient one, so you should be able to just do the characteristic equation, right? I don't know if that's how he would do it, but that's how I'm going to do it. So the characteristic equation is that. So we get lambda. We get that. Lambda equals 0.
Where did you get the lambda from?
Oh crap! Yes, you're right. Thank you. Sorry, that's supposed that would be a lambda if it was dv on dx, wouldn't it? Always get that wrong. I should really pay more attention to the things that I always do wrong. It's like trying to spell.
Left side, right side.
Oh, beautiful. Thank you. And so we get lambda, depending on the actual value of s, I suppose. Sorry?
You can factorise that.
Oh yes, you totally can. Beautiful. Brilliant. Yes, s squared plus 2s plus 1 is s plus 1 all squared. Oh, look at them being nice to us. Okay, and so my solution will be of the form v is something times e to the s plus 1 x, because this was all in terms of x, wasn't it? It was dv on dx, so my answers will be in terms of x. Something like that. Which is nice. Now that a and b are constant with respect to x, which means that they might be functions of s. Oh, good! That's what we're aiming for. Brilliant. Okay. Nice. And so then we're supposed to figure out what the AS and BS are, I presume. So boundary conditions. So we've used the initial conditions, which were these ones. And the boundary conditions are these ones. So technically this is X, S. Now, presumably I should be Laplace transforming these boundary conditions so that I can use them here. I don't know. That sounds reasonable to me. So we have V naught T. And the Laplace transform of sine was s squared plus 2 squared. Now, normally the Laplace transform of 1 over 2 sine 2t would have a 1 there, so this must have a 2 here. So normally if this was a 1, that would be a half, so because this is a 1, that has to be a 2, because we had to multiply them both by 2. Okay. And so what's the deal with the limit? Is that still a limit over here?
It's, yeah, because we're not transforming that variable.
Okay. Sweet. And the Laplace transform of 0 is 0. Yay. Okay, so now let's see. So V naught T, capital V naught T, by the way, that's a little v here. Capital V naught T naught S, when I sub it into this equation over here, would be AS e to the naught plus BS e to the naught, because the x is naught. And that is supposed to come out to 2 over s squared plus 2 squared, because that's what V naught S is. Okay, cool. And the limit as x approaches infinity of Vx is well, what am I supposed to do with that? Like, this doesn't exist when x goes to infinity. Unless, oh, that's okay, cool, I can do that, times the limit as x goes to infinity, x plus 1x, plus bs times 0. Okay, so when I go, x goes to infinity, this one will go to 0, because it's minus s plus 1x, and s is positive anyway. That's the idea between, we know that s is positive in the Laplace transform. So that's e to a negative number, and e to negative infinity is 0, and so that's where this 0 here comes from. And then this doesn't exist, that limit there. So the only way this could possibly be equal to 0 is if as was 0. That limit doesn't exist, that limit is infinity. So the only way that this answer can come to 0 is if as equals 0. And therefore bs is s squared. S is 2 over s squared plus 2 squared, because back in this equation as was 0. Right, and so therefore v x s The a is 0 and the b is 2 over s squared plus 2 squared. Is that. Nice. Okay. This is fun. And so, we inverse the Laplace transform of that. So now it says, by taking the inverse Laplace transform, find the solution. Okay, so we've been working here in X land, and now the x's are still going to be here. They count as constants, and I'm going to have to do a thing. Okay. All right. So, all right. I'm supposed to untransform this. So there's a thing about what happens when you would know what to do with if it didn't have the e in it. So without the e, that would go to like sine 2s, sine 2t, this bit here, without the e. And with the e, there's like a shifting theorem. Right. So is it just me, or have we simultaneously shifted the s and... Oh, crap. I'm just... My fear here is... Let's go to an s plus 1.
Just,
Oh, that's okay. I can deal with that because I can expand that out. Like that. And now, brilliant. And now that e to the minus x is a constant. It doesn't involve s. And so I can just leave it there because constants multiplied in the plus transforms are still there. Right, now I can use my shifting. So I've got a constant multiplied, that'll still be there. I've got an e to the minus sx, so in this case the a here is my x, and I can do my thing. So, let's see. Little d xt. So I know that this would normally transform to side 2t. Just give me some space. This would normally transform to sine 2t. And then I'd multiply by u of t minus the a, which is x. But I'm going to have to do that here as well. Shift this one over. And I'm still going to have an e to the minus x. Whoops, sorry. So this bit transformed to sine of 2t, but this bit meant that we have to shift this over by the thing that's multiplying by the minus s, and we have to times by the u with the same, and the e to the minus x is a constant, so it's still there. And that there is the solution. Brilliant! And that's it. It's not pretty, but there it is. So we've got some sine function shifted over a bit, twice as wide, half the period as we would normally have. Doesn't start till x, and it's damped as well. So that's what it is. Something like, and it flattens out a bit, but it doesn't start till a particular spot. Cool. All right. That's probably as much as I can cope with PDEs for them with Laplace transforms for the moment. I just need to quickly go and have a drink, and I'll be back in just a moment. Okay. So now that I'm back, someone's just asked me to do part C, and I might as well do a good job of this Laplace transform thing. Maybe next year I won't do a revision seminar for Eng Maths IIB. Who knows? Okay. f of t is periodic with periods 2. And when 0 is less than or equal to t is less than 2, f of t is 1 minus t. So presumably it's 1 minus t, the same shape, but not necessarily the same formula as we go along. So I just want to have a picture in my head of what this is. From 0 to 0. Great. It looks like that. That's what 1 minus t looks like. Yes, someone's saying the word sawtooth, that's about right. Okay. Compute f of s, the Laplace transform of t. Okay. Okay. Now there's a thing with periodic functions. That's a thing with periodic functions. I'm not sure what it means yet. We'll figure it out in a minute. But that's it there. And so it says that the Laplace transform of the function that I just had will be the integral, we 1 over 1 minus e to the minus period s, because it says here the L period is L and my period is 2. The integral from 0 to the period of b to the minus st f of t dt. Okay. Just to make my life easier, I'm just going to do this. So I don't keep having to write the e 1 over e to the minus 2s. I'm going to just move it over here and I'll put it back later. Okay. F of t. So, f of t in the zone from 0 to 2 is 1 minus t. So I'll chuck that in. Like that. And that's an integral, so I'm going to have to use integration by parts because it's got two things multiplied together. I could use integration by parts as it stands at the moment. I could also split it into two bits, like the e to the minus st and the minus t e to the minus st. Doesn't really matter. I can use whichever one I want. I have to choose which one I'm going to integrate and which one I'm going to differentiate. The one that differentiates, I want it to become simpler. If I differentiate this, it'll become a minus 1, so that seems like a good idea. I've already used, integration by parts I can only do one way, so I'm going to do it my way if you don't mind. So, okay. Crap. Give me a second. Don't need to mark the t's. There's two functions, g and h, multiplied together. Over here we've got g and h, and then we've got g and h again. Because it's a definite integral, these will all be definite integrals as well. And one of them will be a derivative over here, and the other one will be a derivative over here. We want to differentiate this one, so it's going to go there, and so it's going to be like that. That's how I would do it back in Maths 1A, and therefore that's how I still do it. So where we have Okay, so g dashed is e to the minus st. When we integrate that with respect to t, we'll still have e to the minus st, but we'll have to divide by the constant, so it'll be minus 1 over s. Like that. H is 1 minus t, and when we differentiate it, it will become minus 1. I hope it doesn't disturb you from the fact that I actually filled out this one, these two first, and then did it that way. But in my head, differentiation is down, and integration is up, so I can't put them any other way, because that's how I do it. And so, therefore, we have that 1 minus e to the minus 2s of fs is g, which was minus 1 on s e to the minus st, times h, which is 1 minus t from 0 to 2, minus integral from 0 to 2 of g, which is minus 1 over s e to the minus st, times h dash, which is minus 1. I've just subbed it all in. Now, we can't use any of our fancy tricks with infinity at now because it's only going up to 2. So I'm just going to have to sub it in. So I get minus 1 over s e to the minus s times 2, 1 minus 2, minus 1 over s e to the minus s times 0, 1 minus 0. That's this bit here. And this integral I can just do. So those two cancel each other out. So the 1 over s is still there because it's a constant. The integral of e to the minus st is e to the minus st, only I have to divide by this constant. And so I have minus 1 over s e to the minus 2s times minus 1, that's what this bit is. Minus minus, they cancel each other out. And e to the 0 is 1. So that's what I get from there. And then this bit becomes minus 1 over s squared so presumably I could cancel those two minuses as well. So I get 1 over s e to the minus 2s plus 1 over s plus 1 over s squared e to the minus 2s minus 1 over s squared e to the 0, which is minus 1 over s squared. Okay, so that's what I've got. It's not pretty, but there it is. And then I have to divide by 1 minus e to the minus 2s. Because back here, this was still here. I don't like it very much, but that's what it is.
You can combine those
I probably could combine all of that stuff.
by your equation and then divide through. Yes.
That wasn't a good way of combining it, was it?
I've got, in brackets, e to the minus 2s plus 1. And then,
Like that?
yeah, and then I was going to have in the other brackets the s squared and the 1 over s squared and 1 over s. Because you've got the same terms in the brackets now.
No, well this one's a plus one, that one's a minus one. Have I lost any minuses along the way?
Okay, well, that was
Oh, whoa. Oh no, that happened. That's okay.
you take a negative factor, then you've got two factors on the left-hand side and the right for cancels.
Yeah, but one of them is going to be stuck there, so there's nothing we can do. Yep. Something like that. And then at least one bit of it matches. That's what we're saying. That's a good idea. It's not pretty. There it is. I have the slightest horrible suspicion that 1 plus e to the minus 2s over 1 minus e to the minus 2s is like a fan or something. There's some sort of hyperbolic trig thing that it is, but I don't know. That'll do. That's not too bad. My own sake for aesthetic is that I would prefer to do it this way. Because that makes me feel better. I like both the e's to be in the same spot. There you go. I have MOCD. It's like mathematical. Not necessarily OCD, just obsessive, not compulsive. Or possibly, well, maybe it's just compulsive, not obsessive. Yeah, it's just compulsive. Obsessive means that I would lie awake at night wondering if I was a good person as well. And I'm fine with that. Okay. Right. So we've got about 15 minutes. Is there anything else in Laplace transforms that we're supposed to know while we're at it? Someone's making a nice little face at me and going, yes, of course there is, David.
System of ODEs
All right.
and convolution.
Yeah, I'm not sure if I can do it.
I was going to ask, are we allowed to use things that we haven't been taught?
Are you allowed to use things that you haven't been taught?
And the example that I've got is I've just come across how to do inverse Laplace transforms using residue theorem. It seems to be a lot easier in some cases. If we understand it, can we use it?
It was in the notes. It was in the inverse, the definition of the inverse Laplace transform. It was in the notes.
Yeah. In the end, the definition can say use residues.
Okay, so you're looking at that thing there that says optional.
Yeah, that.
Oh, I don't know.
I wouldn't bother.
When you look at residue theorem, using that becomes really simple.
That's a question for Trent.
Yeah.
I have a feeling he's the one who has to decide how he's going to cope with that. My feeling is that if you did it, he may possibly still give you marks, but he will be in a grumpy mood because you will have done something that's not on his solutions. And so he will not consciously, but he will subconsciously not be as lenient with you. That would be my interpretation of what might happen. Look, I'm probably going to throw up if I stand anymore. I'm sorry, because I have a headache. So I'm actually going to stop there. And I know I haven't dealt with all of Laplace transforms, but I've given it a good, fair crack. Thank you very much. Maths Learning Centre is open for the rest of the week. Remember that not all of us know about Laplace transforms, but as the week goes on, the more staff will be there, and the more chance you'll have of finding someone who knows what's going on with those things. And the best plan is to actually sit together, find other people doing the same course, because then you can do what we did today and help each other with some of those things. Even if you can't be in the Maths Learning Centre and you've just got a table outside, feel free to wave one of us down as we walk past, or run in and say we're out there, and we'll check on you every so often, okay? Excellent.